I think it's a relevant measure and element for radio astronomy. And of course, there are several sources of noise. One of it is the preamplifiers. The origin of the history comes from these two little devices. The one on the right is probably well-known design by G4DDK. It's a ultra-low noise preamplifier, mostly used by moon bouncer. The history behind it is that I have been involved in repairing several of those things. Because the moon bouncer typically, when they mess up with the coaxial switch, they put 1 kilowatt into the preamplifier, and the preamplifier typically breaks up even at less than that. So it happens that Marcello can fix it. So I had a chance to get involved in this preamplifier, and I had a challenge to measure the noise, which is the subject of the presentation. The one on the left is a far more high-level breed. This preamplifier has been designed by Professor Weinreb in Caltech, some of his team, and the scope is for a radio astronomy project, which I will discuss and describe in a minute. So this is the simple technology, homemade amplifier. This is the one on the left, which is serial number 2327. That's the Nevada project, which, frankly speaking, I'm not completely aware if it is still active project.
I'm very sorry, but I'm finding great difficulty hearing this. Is there any chance of turning the volume up?
Me speaking, you mean?
Yes, apologies. I'm having difficulty hearing you. I just wondered if there's any chance of increasing the volume a bit.
I will speak louder. I don't know how to increase the volume from the microphone. Anyway, I'm talking about the Nevada project, which, what is the Nevada, what is, I'm not sure if this is still an active project, but the idea was or is to build in Nevada a group of 2,000 5-meter antenna all linked together to create, of course, a huge radio telescope. Now, one of the base of this project is that the preamplifier of each antenna should perform with a 10K noise limit without cryogenic cooling. This was the challenge of Caltech, to produce and design an amplifier with that performance without cryogenic cooling. The logic of the absence of cryogenic cooling, I think it's very obvious, is money. 2,000 antenna with 2,000 cryogenic cooling, 2 preamplifier per antenna makes up quite an expense. To be able to perform and have 10K preamplifier at ambient temperature, it would make a significant difference in cost. So preamplifier UFC is one of the prototypes of the one produced at Caltech and into a side company to try to reach that performance. You can see here there are some of these prototypes, and you can see the frequency and the level of noise in Kelvin. You can see that they're at around 1,300 megahertz. They are all below 10 Kelvin, which is close enough to the performance that was required for the Nevada project. This is specifically the prototype which I happen to have, the 327. You can see that this is not one of the best performance, but still has at 1.2, 1.3, 10 to 12 Kelvin of noise. Now, what is all this about? To be able to measure noise figure at this level, you have to be absolutely sure that your reference point is accurate enough. And both Caltech and another location, in this case, which is the Italian Institute for Astronomy, are utilizing liquid nitrogen to make the measurement. This setup is now, you can see, is measuring the Caltech amplifier, and it has a switch in between to switch the input of the amplifier from the ambient temperature to the cool down temperature. More in detail, this is my amplifier under the same set. You can see the Maori microwave dual with the liquid nitrogen in it, the switch, and the amplifier. Now, this is the measurement of the Caltech amplifier in Bologna. As you can see here, we are all very close to the measurement made in Caltech. One of the things that I've learned by talking to these people is that when they are able to have similar noise measurement in two parts of the world of the same amplifier, they are all very happy because the measurement of noise is very tricky art more than anything. The system in Bologna you see is pretty simple. The one that I have seen in Caltech is a hell of a different, specially made installation to make the measurement. The fact that in two places they are getting more or less the same number, it's an achievement. Now, this is my amplifier measured still in Bologna. As you can see here, the level of 10K is in the range of frequency is pretty much control. Difference you can see is that my amplifier has a much limited bandwidth compared to the one of the Caltech, which is a much broader bandwidth. Now, where is the challenge? How can we do this at home? If I need to be an amateur radio astronomer, I cannot travel to California to ask Mr. Minette, do you mind? I need to make a measurement. I cannot abuse of the friends in Bologna. So how to reproduce this capability to make the measurement at home within usability? First thing I did is to buy 2 noise figure meters for no other reason, redundancy. These instruments are available, at least in Europe, in the flea market. Last year in Friedrichshafen, there were at least 10 of these instruments sold for 250 euro each. So they are very cheap, relatively cheap, and they are usable for comparison, etc. The other thing, which is very important, is the source of the problem. Typically, all the people that do amateur noise figure measurement, they tend to use this, let me say, quite expensive diode noise generator, which are all typically very well calibrated, but they have fundamental issue. They are very temperature sensitive. So if you measure the noise of something when the heating in the house is at 22 because your wife is cold, you get a measurement. If the wife goes home and you reduce the heat because it's too hot, you get a very different measurement. Now, when you measure noise figures in the range of 2 dB, 1 dB, an error of 0.2 of a dB, you may want to like to forget. When you have an amplifier that has a 1/10 of a dB of noise, the error of 0.25 is basically canceling any validity of your measurement. So what you need to do, you need to address a source that tend to be reliable in any temperature circumstances. By the way, the error that I mentioned is publicly available in all the Hewlett-Packard information. Hewlett-Packard declare the erraticity in this of 0.25 plus or minus accuracy when they describe the measurement made with this instrument. So it is not a surprise to see the errors which we will face when we use this type of noise source for the solution is liquid nitrogen. Our micro doer, again found on flea market, not cheap but not also very expensive, capable of becoming your reliable noise source. If nitrogen liquid boils at 77, so it boils at 77 in Alaska, in France, in Italy, in the US, in South Africa. It's what is called an absolute reference. It's like the meter deposited in Paris at the Museum of Reference. So it's reliable, temperature independent. This is the tour where inside you have the resistor that has to be brought to the temperature to become the reference. And this is the filling. Now, liquid nitrogen seems to be something very dangerous I don't want to talk about. Of course, I would not recommend to take a shower with it, but there is a much higher risk to get burned. This would be boiling water than nitrogen for a very technical physical reason. The heat capacity of the liquid nitrogen is very small. So a drop of liquid nitrogen on your hand will do nothing because it will evaporate with a very, very limited amount of heat. A drop of 100-degree water will burn. So it is not so, still you have to have some measure, protect yourself, but it is not so dangerous to get familiar and to use it. The container on top is a doer, which is the vehicle which I'm getting the nitrogen liquid. Nitrogen liquid is used by doctors mainly for a lot of things. It's used for conserve tissues for analysis. So it is not very difficult to obtain. The doer is buy it on Amazon, and then when you have it, that doer will last for about a couple of months. So you have enough supply of nitrogen to fill regularly your Maori to make the measurement. In Italy, that doer costs $50. So it's not an expensive. It allows me for a month and a half of measurement of different amplifiers. So once the doer is filled, you let the system stabilize in temperature, and then you have here the different way of connecting. One philosophy that I have adopted in this is keep it simple. So I did not want to put a relay like the people in Bologna did. I'm just removing and reconnecting the amplifier to the cooled or to the room temperature and then take the measure. This is practical things. It takes time. It's more time consuming, but the driver of this is to eliminate the uncertainty introduced by the relay, by the switch, by the connections, and a lot of other things that you have to control in this measurement. Simple, two formula, the LNA on the measurement, connected to 70K, connected to 300K, the two formulas, and you get, it's very, very simple, very, unless you make mistakes, of course, it is also relatively error-free methodology. the two instruments, the same preamplifier, you will see there are differences. Here, you read 18 tenths of a dB of measurement. This one, you read 90. I'm happy with this difference because 1/100th of a dB of difference is, you know, it's plenty of precision if you want. What is relevant and must be mentioned, I'm not using this instrument. When I'm using it, I am sort of humiliating the instrument. Because this instrument has a lot of capability of making automated measurement in frequencies, in different level, etc. I'm using page 75 of the manual, everything manual. It's complicated, it takes process, you have to do it, you have to be careful, there are a number of steps, but better simple and stupid than using a lot of automation and then getting lost in things that you don't know why it's out of control. So in a summary, the two fundamental temperature, ambient and nitrogen formula. As I said, I'm using in a negative sense the HP 8970 because I'm downsizing its capability. Page 373.79 is the manual page. HP dedicate one page to the manual because you're not supposed to use it manual. You have to use full. I keep it the manual principle. What is needed? A Mauri tour, the LNHB measure, an HP, or there is also an Eaton, similar brother noise figure meter. And I have to say the results are surprisingly coincident and repetitive to those obtained at Caltech. So I'm basically doing at home reliably what I can do if I have to move into these professional places. The Caltech amplifier, from being a measured item, is becoming a reference because I know that that guy does the job. So if I measure with my system that guy and I read what it's supposed to do, then I'm confident that my measuring system is in order and is doing his job. That's all. Any questions?
Well, of course, one question in my mind is the availability of those amplifiers.
Yeah.
I mean, we heard Dr. Weintraub talk about them in previous times, the development of the one at Caltech, et cetera. But I don't, other than a couple that I believe Wolfgang was doing some trial work with, I don't know if anybody else has one of those amplifiers. Okay, and where they came from. Let's put it that way. Where they were available from.
Well, as you have seen in the slides, the series of prototypes of this amplifier have been built. Part of them in Caltech, part of them in a small company near Caltech, and others probably in prototypes. So yeah. The company that built the amplifier for Caltech for the Nevada project is making them. They're not cheap, but they are making them. Give you a few indications. That amplifier has a device which is made in Switzerland. It's a very small company that makes those ET gallium arsenide prototype device specifically for space communication. So it is not a huge company. It's not Fujitsu. It's not Mitsubishi. It's a very small company. So they are also willing to sell the device if you are familiar with doing bonding, etc., which is not easy and simple technology.
Right.
But my answer to your question is the system is open. If you're really interested in that amplifier, the one that you have seen, the Caltech one,
Mhm.
by working with connection, you can find a way to have one made for you, buy one. My opinion is that if you are looking at an amplifier with 0.1 dB with performance capable to do moon bounce, to do pulsar reception, the British design, trimmed with attention to the right device, could perform as well on a narrower bandwidth, but would still do the job. Of course, we have seen technology is go back to the picture. See, they are very different. You know,
Yeah.
you don't want to argue with Professor Weinberg about the N connector, for example. You know, not that one is an SMA. Here, for him, the N is a fundamental piece of all the detail that gets into the device, the FET devices here. Everything else is extremely critical. This seems to be a strip. It is not. The material is toroid, but it's only to support strip. Underneath, there's no copper. It is a hell of a design, and it has a very different level of technology in it. There is a noise generator which can be activated to check. That one, there's a lot more manuality. The strip to prevent auto oscillation is also a lot of trial and error, but you have what you need if you put some effort in. This is an amateur product.
Right.
This is a professional product.
Right.
So you said you can get them, but, and you said they're expensive? Roughly how expensive?
1,000, 200, roughly.
I like 200 better.
But here, you know, it's bought and here to trim those little spiral, the input of the device in this amplifier is not a distributed adapter. It's concentrate, that's spiral. To bring the impedance, to let the device to see the impedance that minimize the noise. To trim those two things between the liquid nitrogen, the wife that is screening and everything, it is not something that it takes maybe a couple of days to get there, you know, after a while. Then the strip, the position of the strip to reduce the auto oscillation is also something that needs to be done carefully, but it's not. The trick of the low noise is that the device, I don't know if you're familiar with this, but the device normally is flat welded to the strip. To introduce and modify the input impedance, I'm not sure if I can do this, but everybody can see, but normally if this is the surface, the device is mounted like this, okay? To modify the input impedance, you lift the device like this, okay? And this amount of lifting is creating fundamentally an impedance on the source. And with that trimming, together with the input circuit, you get the very low noise of the device. So all this process takes a little bit of familiarization of time before you get it to work.
And that's within the ability of an amateur, do you think, to do? I mean, obviously you have a lot of.
I've done it. I call myself an analog electronic engineer. So my enemy is the digital electronic engineer that can do much better job in noise reduction than what I do with my low noise. Today with digital processing, you can dig signal in noise more than by the effort you have to reduce the noise of the input. So there is a competition there, but that's the area that I'm familiar with, so that's where I can work.
How much attenuation is there in the various adapters between the nitrogen source and the preamp input?
Well, there is in my nitrogen source and in the resistance and the connector, there is about 7 Kelvin equivalent of attenuation.
How do you come up with that number? How do you measure it?
Well, I measured it by bringing my system to the professional laboratory and making a calibration of the nitrogen source with their system. So in a way, I have calibrated my nitrogen source, which is exactly what Mauri will do when you buy a new one. But I have done it myself into the lab. So I now know that if inside there is a 70 Kelvin for the boiling nitrogen, my front temperature is 77.
Okay, thank you. One other question. Could you speak a little bit more about the uncertainty of the HP 346 noise source?
The uncertainty is, I can speak in the sense that if you go into the old documentation, you will find documented uncertainty on the aspects of what is the temperature sensibility to the calibration and on the uncertainty of the entire measurement. These are data that I mentioned that are documented by HP, by the origin of those uncertainties these days, I'm not familiar with. I'm only referring to what HP declares for those instruments in combination with the noise source.
So how uncertain is the excess noise ratio typically of a 346?
You are talking about, sorry,
I'm sorry, I was just wondering, typically what's the uncertainty of the ENR of one of the 346s?
here they are talking about temperature sensitivity in the specification. This number, this is the one that you're supposed to put in the machine.
Right.
These numbers can go up and down by 2 or 3%.
Okay.
By temperature variation, by aging of the calibration, there are a number of factors. So if you change in the setting of your machine, only that difference, you will see your measurements changing way above the numbers that you're looking at. You can read the negative noise figures number in something
Right.
because of the error.
Thank you. Very interesting talk.
Have you ever tried to calibrate the noise source using the noise figure it measures versus the liquid nitrogen approach?
I have a friend who does that as a favor to all of those that would like to continue to use this. So it is not a canceled idea to recalibrate this. The problem of measuring things at 0.1 dB noise figures remain because the entire system is still affected by the error.
Yeah, every connector, return loss.
Temperature, you want to take this measurement, you grab this with your hands like this, the number goes down. So you don't have a number anymore. You have just indication.
Thanks.
Okay, thank you very much.